we're going to do the first problem on our first practice exam for exam 3, which is going to be our fun with Play-Doh exam problem. So let's go ahead and read through this and let's kind of work through the solution. So one of the first things that I'm going to do is kind of relabel these axes, get rid of X, Y, and Z, 1, 2, 3. So I'm pushing this in the square die mold. I apply some stress. The walls are much stiffer, so do not deform elastically. So they are essentially rigid walls. They will not move. So rigid. Play-Doh has this coating so that they're frictionless. So that's going to tell us something about our shear stresses. And we want to take the Play-Doh down from initial thickness in the Z direction or 3 direction from 10 to 7 millimeters. So let's write out the full stress and strain tensors for this problem. So my stress tensor, I know definitely that there's going to be stress in the 3-3 direction. There will also be a stress in the 1-1, 2-2 directions. Why? Because the walls are constraining the material as the material wants to expand. And because that coating was lubricated, we could say that the shear stresses are going to be equal to 0. We then know from our strain tensor, from our equation 66 in our notes, that if our if our shear stresses are 0, our shear strains will also be 0. Let's go ahead and get these out. So will there be a strain in the 3-3 direction? Absolutely, and we know that the strain in the 3-3 direction is going to be the change in thickness over the initial thickness. So that's going to be going again from our final thickness of 7 millimeters minus 10 millimeters, the initial, divided by the initial thickness of 10 millimeters. So we'll know that value, but we also know that the strain in the 2-2 and the 1-1 direction will also be, actually will be 0 as well, because again, they're constrained. That material is not going to expand in that direction as much as it might want to. So let's go ahead and solve for this value quantitatively. We also know that we're dealing with Play-Doh, so that's a polymer. So we know that my Young's modulus is going to be 1 gigapascal, and nu is going to be equal to 0.4. So let's go ahead and start solving this problem. So let's go here. Actually, let's start to solve for it. So I'm going to say that my stress equals sigma 1, 0, 0, 0, sig 2, 2, 0, and 0, 0, sig 3, 3. So that's my stress. My strain is going to be equal to 0. Actually, we kind of know those values already, but I know that my strain in the 3, 3, so E3, 3 is going to be equal to basically minus 3 divided by 10. Always divide that, make sure you're in your proper units, but I could do that math fairly quickly myself. And I have 3 unknowns, but I have 3 equations I could write in terms of stress. So I know that my E33, I could set that equal to 1 over, let's define my Young's modulus. Y equals 1 times 10 to the 9. Nu is equal to 0.4. And I also have, excuse me for that pause right there, I have my sig 1 or sig 33 minus nu times sig 22 plus sig 11. There we go. I'm going to copy that, and we're going to know that I'm going to write out some expressions as well. Let's solve for sig 11, sig 22, sig 33. Here, I also know that I'm going to write this expression. This is going to be for my strain in the 1-1 direction. I know that's equal to 0, so I'm just flipping that here nicely. And I know that my strain in the 2-2 direction is also 0, so I'm going to do strain in the 2-2, stress in the 2-2. This is going to be 3-3, and we'll solve for those values. Do those values make sense? They do to me. They're all negative, so they're compressive stresses, and so we have those values. All right. So actually, I'm going to go ahead and let's assign those values right now. Let's say here, so we can get the full stress tensor quantitatively. That's equal to this. That's equal to this, and that's equal to this. All right, here. So now you can look at your stress tensor. You can look at it in matrix form. There we go. So that's that first part of the problem finished. So again, think about if there's no frictionless, or if there is friction on those walls, you might have to consider those shear stresses. So A is done. Write out the principal stress tensor, rotation required to get to this state. Do the same thing for maximum shear. what is the stress tensor for a plane that is 70 degrees clockwise from the principal stress tensor? So I'm going to break this down into planes, but I can also give you the principal stress tensor for the entire 3D state. So I could look at my stress, I could look at eigenvalues, stress, and that's going to be my principal kind of stresses. Actually, we're already in that principal stress state. Actually, so for this problem, we can answer this question quite easily. So we are already in the principal stress tensor, so we're done there. What's the rotation required to get this state? 0. For maximum shear, all we have to do is rotate 45 degrees, clockwise or counterclockwise. And then it's also asking us for what's the stress tensor for a plane that is 17 degrees clockwise from the principal stress tensor. So we're going to break this down plane by plane. So I'm going to kind of say that this is my stress in the 1, 2. It's going to be sig 1, 1, sig 2, 2, and then I know that my shear is this. I could also do the same thing for stress 1, 3 is equal to sig 1, 1, sig 3, 3, 0, and then finally my stress 2, 3 is equal to sig 2, 2, sig 3, 3, and 0, not 9. So I could take each of these. So T dot stress 1, 2 slash dot theta goes to, it is clockwise, so that's going to be a minus 17 degrees. And the other 2 planes, so stress 1, 3 slash dot theta goes to minus 17, and then T dot stress 2, 3 slash dot theta goes to minus 17 degrees. So there we go. Those are just the values that we'll be working with here. So now we could go about actually solving the rest of this problem. So let's go ahead and see what the rest of the question is asking us to do. And you can kind of see some of these values and the different stress states that we're observing here. So stress 1, 3, 2, 3. Yeah. All right. So will this material yield being the Rankine, Tresca, and von Mises criterion? So let's go look back through our lecture notes and let's see. So our Rankine is sigma 1 greater than sigma y. So let's look first at our problem statement is looking at here. So let's go ahead. And it's saying that our polymer material is the red curve here. So I'm going to say that material starts to yield probably somewhere around, so our yield stress is going to be minus 30 MPa. So let's go ahead and quantify this. So for Rankine, I know that my sigma 1 must be greater than sigma y. For my Tresca, sigma 1 minus sigma 3 must be greater than sigma y. And then we have our von Mises, which we're going to have to look back up. So let's go ahead and look back at our stresses. So for our eigenvalues here, so this would be our sigma 1 is equal to sigma 2. So that is about 428 megapascals. So that is much larger, so that will definitely yield. What about sigma 1 minus sigma 3? So let's go ahead and define this. Sig 1 equals this, the less negative value. Right here, that's sig 2 is equal to sig 1. So again, remember, the least negative, the largest of these values, and then sigma 3 is going to be this one right here. So sig 3 is equal to this right here. So sig 1 minus sig 3, that is going to be 200, again, megapascals, so that will be, again, larger than that value, so that will yield as well. And let's look at sigma effective. And again, I wouldn't worry too much about a problem like this on the exam. It's a little bit laborious, look more for those rotations, but let's go ahead and do this math out. So here I can do square root of 1/2 times sig 1 minus sig 2 squared, sig 2 squared plus sig 2 minus sig 3 squared plus sig 3 minus sig 1. You can't see that here, but sig 1 squared, close that off. Then here, so again, that 200 value, again, that's going to be greater than that yield stress. So we are definitely going to yield that material, no question, no doubt about it. So it will yield for all the criterion that we see here. And then finally, Playdoh is looking to make a number of different types of products that boast maximum stiffness, ductility, strength, both types, elastic strain energy, which polymers did you pick? Give numeric examples for ductility and strength for the polymers that you pick. So let's look at stiffest. So stiffest material, clearly based on that slope and linear regime right here, it's going to be black. What has the largest ductility? Well, ductility is governed by these values, so I'd say they're all about equal as well. Strength. So let's look at both types. So both sigma y and sigma UTS. So sigma UTS right here, clearly, or sigma, the ultimate tensile strength, again, it's just the largest value of stress, clearly going to be the black. Also, if you look at the kind of yield stress here, it's probably not yielding until 40 megapascals here. That's also the black. And you can look at those values for ductility. It's going to be, value of strain 0.9. For strength, again, it'd be this minus 120 and 40, or minus 140 as well. And then finally, which has the largest elastic strain energy? We remember in our stress strain curves here, and when you're looking at these expressions, elastic strain energy is going to be what? So my U elastic strain energy volume times integral y sigma e d dE. Actually, well, stress times strain, stress times strain dE, et cetera, et cetera, et cetera. So the area in that curve times the volume. So that's going to give us our elastic strain energy for this problem. Yeah. You can look back to the notes for, let's go ahead all the way back into lecture 12. Let's go all the way back in page 1. And then let's go ahead and find that expression for elastic strain energy here. Oops, excuse me. And you can see here this integrating from there. So there you go. Modulus of resilience as well. So that's going to be those values. Nice. And finally, the question is asking, the volume of the red polymer is 10 times as large as that for the other polymers. Does that change any of your answers to D? What are the units for toughness? Well, toughness, we know, again, so toughness, 0 volume times 2 strain at failure, stress times dE. So again, stress units of pascals or Newton per meter squared. I multiply this by my volume, meters cubed. A Newton meter, those units are going to be in joules. Makes sense, right? Energy, toughness, energy required to break the material. And then finally, does this change if your answers to D? The only answer it will affect is that elastic strain energy, because again, the volume could be different. So we might choose, if red is 10 times an order of magnitude larger, we might consider that being the largest elastic strain energy of that material. So that's the first problem done. So hopefully pretty straightforward. Please let me know if you have any questions, and we're going to get into thin wall pressure vessels, my pipe burst next time. So I'll see you all in the next video. Thanks. Bye.